So, good evening. So, today I will be conducting the week 10 live session of the course of CFD. So, we missed the last live session because I was out of town, so I could not conduct it. Uh, I asked if that can be I don't think it would be rescheduled. So like if you have problems from the previous week, then we can discuss it like in a separate live session that can be conducted after the completion of 12 weeks. Okay. Uh, so generally one hour live session is given after completion of 12 weeks where we can discuss like doubts of every uh, uh, all like the whole course. So that can be done. Okay. So today let's start with week 10. Uh, So first we have we will have this 1D steady state convection diffusion equation, and we will find the exact solution. And like today's major topics will be like based on this particular concept of exact solution, and the schemes that we had discussed so far were discretized, and the kind of uh, the forms that we had assumed for the discretized domains were generally like a very random form, maybe linear or quadratic or some other thing, but like we had chosen it a very in a very random way or using a logic which had nothing to do with the equation itself. So now we will see how we can actually use this particular equation to have a knowledge about what we can put as uh, a form, the form of the expression that we are solving in a smaller domain, discretized domain. So first for that we would find the uh, exact solution of this particular equation, and that question is given. So this is basically a very simple differential exercise. Uh, I would request you to try to do this. So you have to basically solve this particular equation. So there is only one independent variable x, and nothing else is there. No time is there, or no y direction is there. So it's simply one dimensional convection diffusion equation. This is the convection part in the left hand side, and this is the diffusion part. Please have a go at this particular equation. So are you making any progress? So firstly, our equation that has been provided is like in terms of phi. We would like to convert it in terms of theta and like instead of x, we want to put y. Hmm. So these are basically non-dimensional terms. So we would first want to non-dimensionalize our equation. Hmm. So let's see uh, how we would do that. We would simply like means put this expression instead of phi and see what extra we have done. So let me. This is one way you can do. You can do it in any other way as well. So rho u, and if I simply write it down like phi minus phi 0 by phi l minus phi 0. So you can quickly see that phi this minus phi 0 is okay because that is a constant. If you take the derivative, it will be 0. But this phi l minus phi 0 in the denominator, that was not there previously. So you have to multiply that. Similarly, in this side as well. Hmm. So ddx gamma. So I'm directly writing d theta dx, but there is a phi l minus phi 0. What else? We have to substitute this x for x by l. Hmm. So let me try to do that here itself. So instead of this x, we would have y, which is x by l. So there will be 1 by l. So very similar for the rest two derivatives. That's where our like value of x is there. So now you have theta and y, and the rest of the values are given. So L is given, rho is given, and gamma is given. Uh, so try to solve this equation.
Till now, we have come across several convection diffusion.
So has anyone solved it? Hello. So I'll do another step. Please like try to attend this. So rho u I'm assuming to be constant. Rho u L and also gamma I'm assuming to be constant. So what else do I have now? D theta dy is equal to double derivative. So now it becomes very simple to solve. It can be very well seen that this will take a form of a exponential function because like one of its derivative is has the same form as its own like a higher order derivative. And so like we all know like dy dx of if y is equal to e to the power x, we will have dy dx is equal to y and so on. So this also um, resembles a very similar form. Hmm. So before proceeding, we must find out what is this rho u by L. So viscosity is given, length scale is given, and density is given, and velocity is also given. So this what is this value?
4,000.
This is 4,000. Okay. So have you converted the units?
No,
I,
no, no.
yeah, you can like see that the length scale is in millimeter. So you can also write down the units so that you know which units will cancel out.
I think 4.
This is coming out to be 4, right? So
Yes.
probably it will be 4. Let's finish doing this.
You get 1 hour 0.25, nothing but 4.
Hmm. So all the units are getting cancelled, and here the remaining is 4. Hmm. So what will be the answer? So 4 d theta dy, this is equal to d square theta dy square. So what does this imply? If I integrate it once, what will I get? Let's create another page in so that we can discuss this.
4 theta is equal to d theta by dy.
Yes. How should we proceed solving this? So we have got this, like, uh, let me put it a page. Yes. So now we have got this. 4 d theta dy is equal to d square theta dy square. So this is basically, the second term is basically d dy of d theta dy. So you can see very readily this is 4y equal to ln d theta dy plus some ln c, right? So this is after integrating. So what we did, we just like redistributed the terms and right. So we can change this into a form of an exponential, and that's what we do. So d theta dy, if I like keep it in one side, then this will be 1 by c1. So additive logarithm, so this will be c1 d theta dy, and if I take anti-log, then the whole thing will be exponential, and the expressions with log in, with a log will will be simply that expression itself without the log. So how much this is? This is 4y. Again, we need uh, same an integration. So this will give us 4 c1, 4 by c1 e to the power 4y plus some c2, which is integration constant. So we have not put the boundary conditions yet. Except that also you can see that this is a uh, this is giving us this exponential form. And so far, while solving this kind of a convection diffusion equations, we are discretized and taken linear forms. So that might result in some error, or like we need to discretize very finely to obtain accurate results. Whereas if we have if we know a form of a solution to a convection diffusion equation, we can use that particular equation to create the surfaces. So let's put the boundary conditions here. So phi 0 is like we can have phi 0 here. So that means theta at 0 is 0, right? If I put phi 0, this becomes 0. And similarly, theta at L, this is 1. Hmm. So if I put y is equal to 0, then this is 4 by c, uh, which is 0. So this is 4 by c1 plus c2. And if I put y is equal to L, I even uh, if x is equal to L, then y is equal to 1, right? If x is equal to L, then y is equal to 1. So I will put y is equal to 1, and this value I will put as 1. So this becomes 1 equal to 4 c1 is 4 plus c2. So from these two equations, we have to find out the values of c1 and c2 and substitute it. Please let me know if there is any like calculation error or something. Can someone say the final expression so that we move to the next question?
So is it correct? I got so the value of C1 214.39.
Can you repeat what you got?
So I got the value for C1 to 214.39.
C1 you got
214.39.
214.139 and C2.
See, for C I have not found out. Just I find out for C1. Okay.
So can you find out what is this 4 divided by C1? How much this value is so that you can compare with the coefficient of E2 or 4y. So you can see in the options you have different kind of coefficients in the of this particular exponent. So like from seeing your result, you can be sure that 0.25 and 4, these are not the not the options that you are getting. But can you check whether this is 0.091 or not? So is it the same value? Yes, is it the same value?
So which one, sir?
This 4 by C1, what is the value of this?
C2, huh?
No, just tell me the value of 4 by C1.
4 by C1. Okay, okay. That is 0.0186.
Yeah, so this is coming out to be 0.019, right?
Yes,
This is coming out to be 0.019. And you know that this is nothing but minus C2 from this particular equation,
yes, yes.
right? So you can put it here, and if, this option B actually is matching with the option that you are getting, right?
Okay.
So you can like take this particular equation. So when there is convection as well as diffusion, we tried like as we solved this analytically, we can see that this actually gives us exponential kind of profiles. So for that we have, yeah. So for that we have an exponential scheme. So this is pretty much like a control volume like method with an assumption of the exponential profile that we like get from our uh, this analytical solution. So there are a few like statements written about the exponential scheme. So can you please like tell me which one of them are true and which one of them are not?
124.
So 1 2 4. Okay. So the what is one? One is like it involves the assumption of an exponential profile for the dependent variable between grid points, and this is correct. This is definitely correct. That's what the scheme is. It is based on the exact solution of the governing differential equation. That is also correct. And like due to its accuracy, it is preferred over the other schemes. So why you are saying that this is not correct?
Because it is expensive to calculate exponential terms.
That is correct. So that's the fourth point. So it is seldom used since calculating exponential fractions is like computationally expensive. So like we generally use Taylor series expansion to get a like a close enough value, or some other techniques also may be used. But this is computationally expensive. This is like not as simple as dealing with linear profiles. Uh, so, so the number four is correct, and number three is this wrong because this is actually not preferred over the other schemes. Okay, so 1 2 and 4 are correct. Yeah, so 4 2 and 1, and this is like means it will be accurate, but this will be very computationally expensive. That's why it is not preferred over the other schemes. So this is the correct option. So let's go to the next one. So there is also like a hybridized scheme where we try to make this more computationally feasible. The method more computationally feasible. So what are the characteristics of that method?
So it is 2 is it neglects diffusion when Peclet number becomes greater than 2.
Hmm. Yeah. So that is a tactic that is used here. So it neglects diffusion when Peclet number becomes greater than 2. So if Peclet number is high, we will have more like the effect will be more convection dominant. So when Peclet number becomes greater than 2, in this particular method, the diffusion part is neglected. What else? Here also, like we do not directly use exponentials. So we like convert the exponential terms to more sort of linear functions. So that our computation becomes easier. So so one and two here are correct, and it involves the division of entire possible peculiar number range in four regions. Uh, is this correct?
No, no.
Okay. Hmm. So how many regions?
Three.
Yeah, three regions. So high, yeah. So so this is four regions is not the correct option. Hmm. So this is option one and two. Okay. So what does this question say? Consider the advection and diffusion of flux J, a variable phi, across the interface of the control volume grid points I and I plus 1. So that is shown here. So this interface E is given, and across that the flux is shown. So and the flux is non-dimensional by the diffusion stretch. So what is the flux given by? That is the uh, first statement. So, can you tell me these expressions of A, B, like what are these A and B?
This is coefficients of advection convection.
Hmm. Okay. So, what are they denoting here? So, how is that related to the flux of the this particular interface? Yeah. So what are A and B here? So A and B are the coefficients of the these grid points, which like corresponds to the amount of flux going through the interface, right? So here the flux going from I to the I plus one cell, so that will be multiplied, the coefficient that is multiplied to get the amount of flux is V. Hmm. So this way, so this is going this side, and this A is similarly multiplied with this phi 1 I plus 1 to get the flux value across the interface E from the other side. Hmm. So the total flux that we will have from this I to E in this particular direction, in the direction marked here in blue, we would have this B5 phi I minus A phi I plus 1. So this contains the contribution from both the sides. Okay. So what about this phi E? So phi E is basically the phi interpolated phi value that we can find at the interface. So if you want to try to represent this particular like flux in terms of this phi E, then we would use P as the coefficient. So P phi E. So if we like represent it through like the same units, like means the same non-dimensionalization, then this phi P phi E and these two terms. So these two terms, the difference will be the diffusion strength, the amount of diffusion. Hmm. So that way, you this particular equation that is being given, this actually does not make sense because we do not can directly relate these two terms. We will have these coefficients here, and these coefficients will depend upon the kind of profile that we have chosen for these different elements for these control volumes. Hmm. So the flux for the flux, these are the coefficients. But if you want to like get rid of the grid point values and like simply relate the coefficients, then this will not uh, this will not happen. We will need the profile assumptions. So which are the correct statements here? Correct statements is 1 and 2. So the third one is like we will not be able to arrive at this particular statement. All right. Okay, so let's go to the next question. So, which of the following relations between A and P are true in context of generalized convection diffusion formulation, where the non-dimensional flux across the interface between the grid points I and I plus 1 is given by this? So yes, we encountered this in the like last problem itself. So oh sorry, I was muted. Is the first one correct? BP is equal to A minus P. So what does P and minus P signify in this case? So this is basically signifies the like change of direction of like the flux direction that we are talking about. So remember P like is relates to the flux at the interface. So if I take the interpolated value of phi at the interface, then the value of the flux will be computed using P. So if P is like the sign of P is changed, that means the flux has been reversed. So in that case, what would happen? So in that case, whatever the flux that was coming from like B, so I to I plus 1 would go to I plus 1 to I, since the direction that we were considering has changed. So BP must be equal to A minus P. So when the direction is changed, that will itself become A. So this first one is correct. What about the second one? Second one is not correct because like those two have nothing like relating each other. We need to find out the values of both to uh, get to a solution. Is any other option correct out of the like the other two?
BP is equal to A module P plus maximum P comma 0.
Okay, can you explain?
No, yes, sir. Difficult.
Can you explain how this like comes out to be?
I guess it's
Sorry.
I guessed it.
Okay. Can someone else explain? So what you said is correct. So these two options will be correct, but like you need to know the reason behind this. So this is very clear. Why is this coming out to be? Uh, but this is not very clear to me. I need to look into this. Hmm, Okay. So, I'm stopping here today. So we have not like covered the whole portion of the week 10 in this session. So we'll try to like go quickly in the next session and try to catch up uh, to where the means the current portion that is going on. Okay. Like I will meet in the like next session, and I will try to upload the videos also. I think last two sessions videos are yet to be uploaded. I will try to upload that. So I'll stop here today, and I will like continue in the next week. Okay.
Thank you,
Thanks
sir.
for yeah, thanks for joining.
Thank you, sir.